welcome back to the second tutorial by Professor Ketan. He is currently with the Department of Electrical Engineering. Earlier, he had done his PhD from University of Minnesota. Has been recipient of multiple awards, including INSA and Scientist, Shelter and Fellow, Research Fellow, INSA Certificate Fellow, and many things. And he has also been on the editorial board of my. So he is going to speak to us on optimization.
Okay, thank you. Thanks for the introduction and hello everyone. Good morning. 4 minutes remaining, so let's start. So this tutorial is on optimization, and the way I have structured it is that it is really starting from the basics. So if you are familiar with optimization, you will get a bit bored, at least initially. So I hope that through this tutorial, all of you who don't know optimization or have not seen of optimization easily whenever they need. Right? Still, if you think that I am going to fast, you just please let me know. Just trying to modulate myself to whatever level is best for this room. So that let's start. Okay. So in this, I will cover basically some line. It could actually involve a little bit of curving going around. Essentially, you could say riding the currents so that it reaches the goal quicker or with less energy, right? So this is example of a optimization problem. And the optimum value is this energy optimal path is the green one, while you could say that the straight line path is your analytical solution ignoring the ocean currents, right? If you ignore the ocean currents, then that is your analytical solution, right? So I hope this is just to motivate the optimization framework, and this is not easy, this is complicated, and therefore some algorithm has to be used. You cannot find the green one analytically. Even if you know the analytical, I mean, somehow if you know the analytical way the ocean currents vary, then also it is not easy to find actually the solution of this green or the formula for this green trajectory. Right. So let's continue then. From the ocean navigation problem to the optimization algorithm, let's say a flow chart. So what we generally do in all context, be it ML or be it any system, any industry, you start with a design specification and an initial design. And then there is an algorithm which actually evaluates whether that design is good enough. We tune it a little bit, right? If it is good, then we are done. If it is not good, we tune it a little bit and tune the design till it is good with respect to some metric generally. And then that becomes our final design. And this is a very simple framework. You could make it complex also. You could add more steps here, but this is very simple for you to understand that this is how optimization will generally work. We'll not generally have the luxury of finding the optimal solution analytically and substituting. We'll always use this approach. Okay. And this brings us, this flowchart shows us that if your design is not good, suppose it is suboptimal, then what is the reason? What could be the reason? It's not always that, it's not always one reason, right? For example, your problem could be misspecified in the sense that you have the wrong problem you are solving for something else. So that is one cause for suboptimality. Your initial design could be very, very bad, right? You have to start with some initial design. So therefore that initial design could be very bad. Your algorithm could be unsuitable, right? And finally, you may be implementing it wrongly, right? So again, related to misspecified problem, right? So all these are possible reasons for suboptimality, but when we talk about optimization, we are only concentrating on this part. We are only concentrating on the algorithm part. Assume that everything else is correct. Everything else means design is correct, problem is well specified, implementation is correct. Okay. So let's look at that. Unsuitable algorithm. So this is what we want to avoid, first of all, as optimization. As someone who knows optimization, I would like to avoid to use an unsuitable algorithm. Okay, so writing down an optimization problem, this is generally how it is written, the standard form. Here f of x is some function which is called the objective function. X is usually a vector, so x is the called optimization variable, usually a vector, and then p is called the optimal value, right, the minimum value, and p can also be written as f of x star. So what is x star? Another way of writing the same problem is x star equal to argmin. So argmin is saying that the argument of the function, that is the smallest. X star is the solution or the minimizer, right? So these two are saying the same things. If you ever see this, don't get confused. Okay. So just to start with very simple toy example, x minus 2 square, we already know that the solution is 2. And if you plot it, then you can also see it, right? So by plotting this kind of function, you can see the optimum, right? In practice, we cannot obviously use this method, which method? Which we cannot plot and then look at the optimum. Why? Because the optimization variable will generally be in Rn. So it's a vector, which means that you need to plot in n dimensions, which is not possible beyond 2, right? And plotting the function may not also be a good idea. You know what you are doing when you are plotting, you're actually evaluating the function at lots of different points, very close points, and then drawing a curve through them, right? Which is also not necessarily a good idea. In fact, a good algorithm will be one which actually needs to evaluate the function as few times as possible. Not, hundreds of times along every axis, but as few times as possible. Right? So this is one thing. And if I give an example, very simple example of fitting a curve through some points, fitting a quadratic function, for example, through some points. This is covered in the, has everyone seen this problem? Least squares problem, or you could say linear least squares problem. You can find the analytical solution in some cases. If A is invertible, definitely, or A transpose A is invertible, then also you can find it. Otherwise, if these two are not the case, then you need to find through some other way. For example, you can find through singular value decomposition, right? So I'm not going through these, linear algebra. I assume that some of you know. Even if you don't know, you can just believe me that you can find through linear algebra, right? The challenge here in this analytical solution, so this is an interesting one. The challenge here is that its complexity is order n cube. Now, what do I mean by that? Its complexity depends on the cube of n. N is what? It's the size of x, right? So size of x. So complexity is cube of n, and of course there are other constants which are multiplied by n cube, which I have hidden in this notation of O. Right? There are constants that depend on the accuracy to which you want the solution. There are other constants. I have just hidden them. Okay, so complexity here is order n cube. But the question here, we have an analytical solution. Still, you may say that I want a faster algorithm. Maybe it can be less accurate, I don't care. I want a faster algorithm, especially for the case when n is large. Imagine n to be 1 million. Right? 1 million cube is how much? Very, very large, right? 10 power 18. So we don't want that much complexity. I don't care about the accuracy. I can live with less accuracy, but I just want to run my algorithm in the first place. Right? So that is also, so there are also lots of optimization algorithms, iterative ones, which take less than n cube, like order n, and still work. Right? So this is another motivation for studying optimization algorithms, even if you know the analytical solution. Okay, just as a notation, just to clarify the notation, maximization problems can also be written as minimization ones. So if I have a problem which involves maximization, these are two different ways of writing it, then it can be related to the minimization problem like this. So you put a minus sign here and here. And in this case, you just need to put a minus sign here. Right? So the maximization problem can also be written as a minimization. So I don't have to separately deal with maximization problems. I'll just only say we have a minimization problem. If actually you come across a maximization problem, just write it as minimization of minus of the objective. Okay. Okay. Then there is the issue of constraints. In design problems, often we have constraints, more often than not. For example, fair machine learning is one example. Have people heard about fair machine learning? Fair machine learning is all about removing the bias from machine learning. If machine learning, you pose machine learning as an optimization problem, then you can pose fair machine learning as a constrained optimization problem. The constraint being that it is not biased. For example, if you are using machine learning to hire people, then it should not discriminate between male and female. That is an example. So that is a constraint that comes into the problem statement or the design problem. And the objective is the same, which is the machine learning objective, minimize loss or whatever. There are also similar constraint problems in lots of different areas. It's a huge area of study, constraint optimization. So for example, image reconstruction, we have non-negative version of least squares. The least squares problem is the same, but now X is required to be non-negative. And then similarly, parameter estimation, if you do ever, you look at lots of distributions, right? You have to estimate some parameter that is ultimately an optimization problem. And there you have constraints such as variance being positive, right? Particularly when you are doing from data, you may sometimes need to impose that constraint, especially if number of parameters very large. Okay, so constraint can be written as gx less than equal to 0. So some function has to be less than equal to 0 or greater than equal to 0, something like that. Equal to 0 also, another possibility. If you have multiple constraints, then all of them you can put together. So this would be a general form of a constraint, inequality constraint optimization problem. Similarly, you could have equality constraints. Right, and ST I have written, that stands for such that. Another way of writing, sometimes you will see this in, especially in mathematics books, which is that minimize f of x subject to x lying in some set. And that set is actually describing all the constraints that are there. Right, so just two different ways of writing. Not that one is simpler than the other, because these are two different ways of writing. I mean, I'm assuming that you can write it in this form. Okay. Any questions so far? Okay. So if we look at a simple example in one-dimensional case, the constraint would look something like an interval, right? And you have to minimize x. In that interval, you may say that either it is this point or this point, something like that. So maybe it could be this point. While globally, this is the minimum. So because it is constraint in this interval, you need to find this. Again, some more terminology about the critical points. So this is the global minimum, the green one, which is globally toward the function, it is the minimum. And this is the local minimum. And these are the local maxima. And then there is also a saddle point. Right, so this is some terminology. Generally, in practice, what we know from several years of research is that global minimum or maximum is difficult to find, or even analytically they are difficult to find. Numerically also they are difficult to find. It is easier to check whether a point is local minimum or not. Most algorithms that exist today, they just stop when they find the critical point or critical point. All of these, any of these they find, they just stop for most algorithms. But you could do some modifications to identify whether those are local minimum or not, because ultimately you want local minimum or global minimum. You don't really want global or local maximum or straddle points when your goal is to minimize. Right? So some checks you can do to ensure that the point is local minimum. Right? So generally you can check if it is a local minimum and restart otherwise. That is one possibility. Right? And then we are looking at, in this tutorial, we'll only look at continuous variables. At least in machine learning, everything is continuous. Most variables, the way that is posed is continuous. Problems are there with discrete or integer variables, especially in logistics. So that we are not covering here. It's not that it is not important, it is very important, just not covered in this tutorial. So usually they are much harder also. Integer programming problems are much harder. So we'll not consider that in this tutorial. Okay. And let me also motivate some examples in ML, just for those who have seen this link. It will be very simple. So linear regression is one example. But different from classification, the goal is to predict real valued variable in regression, and independent variable vector is again a variable x in RD, and we want to predict y, right? So for example, we could say whatever we want to predict takes this form, W transpose X plus B, like linear combination of X values plus a constant. And there is a training set. So when we talk about ML, then this training set, testing set, those become the new terminology that is required. So there is a training set, there's some points that are given to you. And based on this, you can solve this optimization problem, right? You can solve this least squares problem, right? The minimization is with respect to these parameters W and B, right? So W and B is what you need to find. Xi, Yi are given to you. And for example, if we look at 2D example, X would be one dimensional and Y is one dimensional, 2D. And in 2D case, it's just a best fit line, right? Their points are given, you just have to fit a straight line through those points. So least squares formulation would be something like this, and you can write it in the vector form, right? So I hope people are familiar with the vector form. For all vectors, I've made them bold for you to easily distinguish. So how do you write this in this form? Right. So here optimization is with respect to the vector U. Here optimization was with respect to W, B. So often I will write optimization problems in vector form. And if you have not figured out, here is the solution. You have to stack y1 to ym in the vector y, stack wb in vector u, and x will basically be x1, 1, x2, 1, and so on. Right? So matrix multiplication will give you x1w plus b, x2w plus b. Right? So once you do that, then the problem is written in this vector notation. So generally in optimization context, vector notation is preferred because it allows us to not worry whether something is scalar or vector. Just assume everything is vector. Right. So this is, by the way, I have written down the closed form sort of solution. In this case, it is simple enough, so you can derive it. So if you are seeing this for the first time, please do derive it. It's not very complicated, but do verify that this is the solution. Okay. Just also showing you some code. We'll go more into code tomorrow, but just showing you some code for the sake of it. This is for predicting stock prices. Now, if you don't know Python, you can just copy paste into ChatGPT, ask what it is doing. So that's how I do it generally. But yeah, but it's very simple. I mean, if you read it, you can just understand. So it's basically taking a table, removing one column, and that becomes our column that we want to forecast. And essentially that becomes, from there, we can get the features, the target, and then we are applying a particular kind of inbuilt algorithm, NP, linear algebra, LST, LTS, sorry, LST SQ. So that stands for least squares, yeah. And X train, Y train, that's it, right? So if we look at something like Python, which has lots of libraries, everything about optimization is hidden, right? Where it is hidden, where is the optimization happening? Somewhere in this LST SQ, right? So tomorrow I'll share all the links because I'll share a lot of codes, but today I have not shared it. Sure. Sure, I'll share tomorrow. Or today I'll share, but you can run it tomorrow. Right, so this is very simple. My goal is not here to show you exactly the code. We'll go more into code tomorrow. So if I do this short stock prediction, this is I think stock prediction like at the end of the day. So It's also very accurate, interestingly. And this is the data set is taken from this link. Right? So it's a very simple example of optimization, how to do it. Not a long code, very short code, and all steps are easy to understand. So now, once you understand this, you can go into depth of it. That what exactly step is doing. How do I change something is not working? How do I change it? Any other questions? Some more examples. So, empirical risk minimization. Heard of this term? This is the cornerstone or workhorse of modern machine learning. So, for example, this is a spam classifier. Mails come in, and there is a classifier which classifies them as spam or not. And for learning such a spam classifier, you need lots of training data, and you have to convert that training data into some vectors. You have text emails, you have to convert them somehow into vectors, and then you have to have each of these vectors will represent an email, and you have to have a label. Let's say spam or not spam, or they call it ham, spam ham. This could be 1, 0, right? 1 for spam, 0 for ham, right? And you could be building a linear classifier, for instance, or non-linear also. And therefore, if the email input is this output could be something like this. What is this? Not sigmoid, it is sine, sine plus or minus 1. So here y1 is plus or minus 1, right? So we are just calculating whether W transpose X T, XT is the test email, plus B is positive or negative. Right? If it is positive, I classify it as y equal to 1, and negative then minus 1. Right? And what you would want is for training email with features X and label Y, predicted label is this, and the error is what? So error is 0 whenever the predicted label is the actual label from the training set. Whatever the predicted label is the actual label, and error is 1 otherwise. This is just an example of a loss function. L is called the loss function. There could be many other similar loss functions. So this is the ERM formulation. So you just remember it whenever we do any kind of or most kind of supervised classification, supervised learning, we always end up with this kind of structure. There's always a 1 by m summation, and then the loss function evaluated for individual training examples. So if you have 10,000 examples, there are 10,000 terms in this summation. Right? So just remember that. Or if you have 1 million examples, 1 billion examples, there are that many terms in this summation. That's why it is complicated. That's why machine learning is difficult, because there are so many terms. And just to add that there could be other loss functions also. Okay. So if you talk about a general classifier, in the most general case, that was a particular example. In the general classifier, the predicted label would be FWXI, right? So F would be a function, W would be some parameter, and it acts on Xi. Xi is the feature vector which represents, for example, your email or your image or your text, or it could be any feature. So predicted label is always written as FWXI. And one particular example of FWXI was W transpose X plus B, that is the linear, or you could have a quadratic term. Quadratic means it depends quadratically on X, and then it could depend non-linearly on W also, right? So all sorts of examples are possible. And neural network, right? Neural network is one such example of the FWX. It's just a complicated way of forming FWX, right? It's a complicated, nested function, just representing one function FWX. And the training loss, again, loss could be anything, 0, 1 loss, like we saw in the email example. It is either 0 or 1. or it could be 0 and then gradually increasing, like the hinge loss or square loss. All sorts of loss functions are possible. And we would form this kind of ERM problem. So if we do this in Python or any software, you would typically have with you available a library, and that library will take all these options. What kind of loss function you want to choose, what kind of FWX you want to choose, what kind of, there'll be, hundreds of options usually, and you have to choose one of them. So when you get more into that, you need to actually know about all those, the strengths and weaknesses of each loss function and so on. But from the perspective of optimization, when we are focusing only on optimization, all I need to know is, okay, there is some loss function, there is some FWX, there is some objective function. How do we minimize it? Right? So we will not worry about specific loss functions. We are more about classes, huge classes of loss functions. Right? So we'll, for example, look at loss functions that are smooth, a big class. Right? So we'll just worry about classes of loss functions rather than specific loss functions. Right? So this is the ERM problem, empirical risk minimization. And the 1/n summation, as you can imagine, is essentially a proxy for the expectation. Right? So m is going to infinity, then this is really the expectation. M is never infinity, but as m is larger and larger, this is a better and better approximation. Okay. Again, spam classifier code. I just took it from internet only, but I hope it's like very easy to hear, to read. In particular, everything about optimization here is hidden behind this one. This is svc.fit, sklearn.svm.svc.fit function. So this is just hiding all the optimization details. Okay. Okay. So I'll just also give briefly, I'll talk about random and grid search. Before that, any questions? Okay. So random and grid search, I'll not go much, just a few slides, because this is something that most people do it or have to do at some point of time. So we should know what it is. So these are essentially search algorithms. Optimization is indeed a search for the minimum or maximum optimum. And sophisticated algorithms are generally much faster. But sometimes we use very simple algorithms just because, either it is not very important to use a sophisticated algorithm, or we can just get away with using a simple algorithm. Sometimes that is the case. So this is called native search algorithms. So simple to explain and implement. Yeah, implementation complexity is also simple. So that's another reason. We don't want to spend a lot of time implementing it. Just quickly implement it, check it. Generally, they will take more time. So random and grid search will take more time, and they are inefficient overall. And but they serve as baseline often to compare with sophisticated algorithms. If you are familiar with machine learning, you will know that many times several of the hyperparameters are searched like this only. We don't bother about actually writing optimization routines for that. Just search, just do random search, grid search. Right. So we'll look at random and grid search, and if exhaustive search, if search space is small, then exhaustive search is also possible. This is for discrete. Okay. So how does random search work? Just start with some infinity value. Repeat as many times as possible. Select a random value of x. Right. Remember, our problem was minimize f of x. So select a random value of x. Calculate f of x. Right, and pick the minimum of the two, whether the stored value is minimum or the f of x is minimum, and that's your algorithm, right? Of course, this is highly parallelizable. You can just, calculate your f of x at multiple machines, and then, once in a while bring them together, pick the minimum. This works better if input space is compact. Obviously, if you are searching from minus infinity to infinity, it's not going to work so well. Or if we know that the optimum lies in some region, then you can restrict your search to that region. And if fx can be calculated efficiently, then this is very fast, right? So for example, if you have a small formula to calculate f of x, or quickly you can calculate, then this is very fast. Right, so this is the code for that. Now this code is not very complicated. I am just importing the libraries, defining the objective function. In this case, it is just x square, and selecting some samples in a particular range. This is one dimensional, right? So selecting some samples between -5 and 5. 100 samples between -5 and 5. Right? And then what do I have to do next? I will evaluate the objective function at those samples. Now I have defined my objective function so that if it can evaluate for the entire, all the samples in one go. Right? Or, I mean, if it is not defined like this, then you have to use a loop to go to each sample and then evaluate there. And then I'm calculating the smallest value. Okay. This is very simple random search algorithm. And then I'm printing and visualizing the results. I'll skip the printing and visualizing part. I hope everyone understands how to visualize. You just have to plot it. So this is the visualization I will get, right? So all these points are where I evaluated, and this is the optimum value I got, right? So all the things that I mentioned about optimization, they are visible from here. First of all, this is definitely better than plotting, because in plotting I have to evaluate a lot more points. Answer is inaccurate, right? Not zero exactly, it's inaccurate. Or this is not zero also, this is also inaccurate. And each time you run, you will get a different answer. It's another point about a random algorithm like this. And I would leave it up to you to check it. This is very simple to do mathematically, that whether your result will change with number of samples. Right? So for example, if I make the number of samples 10 times, what will be the impact on the result? So please think about it, and we'll revisit maybe tomorrow. So what will be the impact of result if I increase the number of samples, say 10 times? Will it become more accurate or not? Fast, yeah, fast also. Another point is how fast it will be. It will be 10 times slower, right? But will it become more accurate, and how much more accurate? Right? Will it become twice as accurate or 10 times as accurate? Right? So please try to do it mathematically. Okay. Then another, brother of random search is grid search. Again, widely used in pretty much the same way. Instead of randomly evaluating, we just evaluate on a grid. And grid is sometimes uniformly spaced, sometimes we space it logarithmically. In machine learning, it's very common to space it logarithmically. For example, if you have to search a parameter between 0 and 0.1, instead of searching 0.001, 002, and so on, just space it logarithmically. So you search from 10 power minus 5 to 0.1. So minus 5 to 1, 10 raised to the power. Right? So in Python, you would just write a simple command like this: a range, minimum R, maximum R, and 0.1. So this will give you all these points. 0.1 is the distance between the samples. So that would be the grid. If you do it in 2D, the grid would look something like this. You have to take samples such that both dimensions are covered, right? So in summary, the grid search would be something like this. You are searching the point here. Random search would be something like this, right? Just taking random points and finding the minimum. Okay. Now there is a major issue with grid search and random search as we increase n, and that is called curse of dimensionality. So what is it? You consider x in Rn, right? N-dimensional vector. Then suppose you do 100 divisions per dimension, right? So for example, you are doing grid search and you say 100 divisions from 0 to 1 in each dimension. Then how many number of grid points are there for you to evaluate? 100 raised to the power n, or 10 raised to the power 2n. So as you can calculate it, this becomes impossible to use beyond n equal to 4 or 5, right? So definitely you need better methods. So this is not, I'm not saying that grid search or random search are good by any means, but they are very simple to implement. So that's why we, right? So some references. I hope there's some way to share the slides. I have not shared the slides, right? I'll share the slides with you. Yeah, slides and videos will be on the website, so you can access from there. Okay, then let us discuss something very fundamental. I hope everyone understands it, but let's discuss anyway, which is the gradients. And the way I would like to discuss it is like not go into calculus at all, but just draw some intuition from there so that we can understand directional derivative better. That's where I'm going. So we generally write the gradient of f as gx, and we write it as df by dx. One way to think of dx is a very small number, and instead of an infinitesimally small number, just a very small number. And therefore we can multiply both sides by dx, and therefore dfx is gx dx, right? So what is the intuition for dfx? dfx is f of x plus dx minus f of x, right? Just f calculated just in front of x and then at x, and take in the difference, right? This is the like a numerical intuition for gradient, for derivative. And if you talk about Taylor series expansion, then f of x plus dx would be, first order Taylor series expansion, then f of x plus gx dx, right? So this is again saying the same thing. So for example, if you have x square, then x plus dx square would be something like this, ignoring dx square. Okay. Now same intuition you can apply to 2D case. So in 2D case, you would have x square plus y square. And in compact notation, you would write d of f of x comma y as this, f of x plus dx, y plus dy, minus f of xy. And if I apply it to this example, then this would come out something like this, which would be 2x dx plus 2y dy. Now, why did I use this intuition? As you can see, 2x is essentially your partial derivative of f with respect to x, and 2y is partial derivative of f with respect to y. Usually a different notation is used for partial, but let's misuse this notation for now, or abuse this notation, not misuse. Right, so dfx y can be written as inner product of these two things. What are these two things? Dx dy is your all these small quantities collected into one vector. You can call it d of capital X, right? And this is what? This is the gradient of f, right? So that there comes the intuition for gradient. Right? It's just a different way of thinking of gradient. So what is the derivative of a scalar valued function which takes vector input, right? F r into r. It is essentially the slope along each dimension. right? So ith entry of the gradient is the partial derivative of f with respect to xi. This is the definition you have seen. I just related it to the intuitive definition that we just looked at. So derivative with respect to xi, while other variables are treated as constant. For example, in this case, look at this, then gradient is like this. And numerically, if you want to evaluate, you would essentially calculate x plus h ei. Ei is what? Ei is the standard unit vector, 0 everywhere, 1 at the ith position. Right? So if I evaluate and take the difference, then I'll get the numerical derivative, numerical partial derivative. So ith entry of the gradient. Okay. And then how do we relate it to directional derivative? So directional derivative is essentially derivative along a certain direction, not necessarily the standard unit direction. This just could be any direction. So what we are doing is we are saying x plus h, h is some very small value, and s could be any vector along which we are taking the direction, right? S denotes a direction because it is any vector, right? So f of x plus hs minus fx by h. Generally, we take s to be unit vector so that it is just only denoting a direction. And this quantifies the rate of increase of the function along s, right? So how much the function has increased from f of x as it goes along s. So that is the directional derivative, right? Another way of writing, so let's now bring all these together. One way of writing of the ith entry of the gradient is the partial derivative with respect to ei, xi, and that is also the, from our definition, that is also the directional derivative along ei, ei being one vector, right? And also the directional derivative along s is basically the inner product of gradient with s, right? So this is interesting. Inner product of the gradient with s is actually the directional derivative, which is defined like this. Another way of writing, I mean, just another way, like lots of different alternative ways. I hope, like if you are confused at any of this, just try to read it and relate all of them together. So G alpha is f of x plus alpha s. And then G prime of 0, if you evaluate, you just apply chain rule, you will actually get the directional derivative along s. Right? So derivative of G with respect to alpha calculated at alpha equal to 0. So just let's take an example. Fxy is x times y, and its gradient is given by yx, right? I hope everyone understands. Derivative with respect to x, derivative with respect to y. Directional derivative along s, which is equal to -1, would actually be minus x minus y. Why? Because you take inner product with -1. And the other formula that we said, G alpha, will give you this. And if you take it derivative, set alpha equal to 0, you'll also get minus x minus y. Right. So if we look at some visualization or some intuition, consider any unit vector such that norm of u is equal to 1. And let us ask this question, that for what choice of u is the directional derivative along u largest? Right? So what is the choice of u for which the directional derivative along u largest? Right? So how do we solve this optimization problem? This is also optimization problem essentially. We are trying to find the u along which the directional derivative is largest. without using optimization algorithm. I'm just trying to solve it analytically. So directional derivative with respect to u is inner product of gradient with respect to u, sorry, inner product of gradient and u, and apply Cauchy-Schwarz. So gradient norm times u norm, and u norm was already 1. So just this is equal to norm of the gradient, right? So when is this? This is upper bound, and when does it become an equality? If you remember your Cauchy-Schwarz inequality, it becomes an equality when, right, they are both scalar multiples. So alpha u is equal to alpha times gradient f of x for some alpha positive. It has to be positive so that the upper bound becomes an equality. It would be negative when lower bound becomes an equality. Right. So this is the equality when in this case. But since norm of u equal to 1, so we can only have alpha equal to 1 by norm of gradient, because u is equal to alpha times gradient. Alpha is a scalar. So norm of u equal to 1, so alpha equal to 1 by norm of the gradient. Right. So therefore, f increases fastest along the direction gradient f of x divided by norm f of x. Actually, norm f of x is just a number. So direction is still decided by gradient f of x. Right. So this, now we have hopefully closed the loop. We started with gradient and directional derivative, and as the direction along which the gradient increases, and now we have said that the direction along which it increases fastest is the gradient itself. Right. So any questions? Okay. So f increases fastest along this direction, decreases fastest along negative of this direction. You can just apply the Cauchy-Schwarz in negative direction, and then same result can be obtained. So this is the figure that is showing the same thing. It is increasing most rapidly in this direction, decreasing most rapidly in this direction. And this is the gradient direction in the xy direction. Remember that third axis, z axis, is where the function is being evaluated, and here x and y is where the inputs to the function. Right. So it's n is equal to 2 in this case. Right. So the decrease and increase is denoted by this arrow, but actual gradient directions are these blue ones. Right. Okay. So that's all about gradient. There can also, of course, be other directions where the function will decrease or increase, which are not the same as gradients. What are those directions? So for example, if essentially any direction u such that the directional derivative is less than 0 means that the function is decreasing. So for example, u equal to minus p times gradient, right? Minus p is a matrix. So the matrix times the vector gradient, the matrix vector product, right? So that the directional derivative is given by gradient transpose u, which is gradient transpose p gradient, right? Now, when is this negative? When is the directional derivative negative? Right. So u is a descent direction whenever this is negative, and this is negative when p is positive semi-definite. Has everyone seen this notation? This is literally the definition of p being positive semi-definite for all vectors such that u transpose pu is greater than or equal to 0. That is called a positive definite matrix. No, so for any, let's say, any possible u, this possibility is sufficient. Any possible u, it is an only. Right. So that is coming from linear algebra. So any direction which is, it just amounts to matrix multiplication with the gradient. that is basically a descent direction. So, and steepest descent direction is of course the one where you pick P is equal to scaled multiple of identity, right? So P equal to alpha I for alpha positive is your steepest descent direction. So I'm just giving some examples in quadratic case. It is simple to give examples. All these figures you can yourself draw them in Python very easily. Right. So these are, several directions along which the function is decreasing fastest, right? Gradient directions in 2D. Right. How would you draw these arrows in Python? You would actually have to select the direction and then draw the arrow in that direction for some length. Right? Then other descent directions. So if this is the fastest direction, then all these are other descent directions. I've just taken lots of different random p values, right? Random matrix p values, and then drawn all those descent directions. Right? Also very intuitive. You can see that it is actually decreasing. By the way, this plot, this blue line denotes the points where function takes a constant value. This is a contour plot, right? So blue line or red line or green line, they denote values where function takes a constant value. And therefore, as you can see here, this is along the third blue line. So all these descent directions are taking it to either the second blue line or closer to the second blue line. Right? So this is one way of, visualizing the different descent directions. 2D in 2D. By the way, if I try to draw it in 3D, then this would look how? It would look like a bowl, right? And but the directions would still have to be depicted in 2D because directions are 2D variables, right? 2D vectors. Yeah, this is the example, X transpose QX. So in this case, it would look like a bowl, but not a spherical, like oval one. Okay. Now, coming back to our stationary point definition, which we were seeing in one dimension. In the general case, stationary point is defined as any point where gradient is 0. Right? So for any function, the stationary point is point where gradient is 0, a differentiable function. So 0 rate of change along all the axes. Right? And minimum is one example. So when the function actually becomes minimum, it cannot decrease any further. So no matter which direction you take, it cannot decrease, and therefore that's called a local minimum, and it's also a stationary point. Right. So this is example of stationary point at the minimum. Right. The minimum point, and the function cannot decrease further. The maximum, interestingly, is also a stationary point. Right. Because the rate of change is 0. The function can decrease, but it stops changing at that point. So the gradient becomes 0. And then there could be like flat valley also. So in the sense that it could be minimum along one direction, but then it could be flat along another direction. Right? So that is also possible. It could be flat along one particular, not necessarily axis, direction. Any direction it could be flat. And orthogonal direction, it could be just a minimum. And then, of course, there is saddle point. It could be minimum along one direction and maximum along one direction. Right? And this is easy to visualize in 2D, but ND it is really difficult or impossible, I would say, to visualize. But therefore, you have to stick to the definition that gradient is 0. And you can, of course, apply this definition that there exists some direction along which the gradient transpose is minimized. There is some direction along which the function is minimized and some direction along which it is maximized or flat. Okay. So This is all for gradient. And this will now allow us to start with our first algorithm, which is gradient descent. Right? Slowly I'm building to gradient. Okay. So gradient descent is a local descent algorithm. Any local descent algorithm works like this. We start at some x and calculate at the tth iteration, you calculate xt. Sorry, given xt, you calculate dt, which is the direction in which you want to move. Right? In the gradient descent, there's a particular direction, but you could calculate any direction in which you want to move. And then you update like this, so xt plus eta t times that direction. So you move in that direction essentially by some factor called eta t, by some scale called eta t. And then, so that is the local descent algorithm. And in the case of gradient descent, we always choose dt as the direction of steepest descent. Right? One thing to emphasize here is that the direction of steepest descent at xt is not necessarily the best direction. Right? So we'll just revisit that point again, but just to emphasize, it's not necessarily the best direction overall. It is just the direction along which the function is decreasing fastest at that point. It could decrease fastest along another direction at a different point. So yeah, may or may not choose eta t to be fixed. Sometimes we choose it to be fixed, sometimes not. Right? And motivation for gradient descent, one could be just greedy search. It's just a greedy way of doing optimization, which is that essentially I am asking this question: find d, find the direction such that xt plus eta times d, right? My next point, xt plus 1, is the minimum possible. I want to go certain distance and I want to find the point where it is, the function is minimized. Right? As d is the direction, let's consider d norm equal to 1. So local descent amounts to solving dt equal to argmin f of xt plus eta d. Right? That's one way of looking at it. Right? But obviously, I mean, I don't exactly want to solve this because I don't want to solve any optimization problem while I'm doing optimization. I just want to approximately solve it. And that's what gradient descent does. It approximately solves this problem. How does it approximately solves? It is basically approximating this function with its first order Taylor series. And once you look at this, you can easily realize that, you know, for small eta, this is the expansion, and d transpose gradient, right? Directional derivative of f along d is minimized for d equal to gradient. Right? So we just need to solve this problem. If I ignore this additive constant, because xt is given if xt is constant. So if I ignore the additive constant, I just need to solve this, and we already solved this. In few slides back, we already solved this. So therefore, the solution, I'm just writing it again, but now in the reverse direction. So d transpose gradient is greater than or equal to this. Did I miss a minus sign? Right, there is a minus sign here. It's greater than minus gradient, lower bound, sorry, not upper bound. And this achieves an equality when it is minus alpha gradient or alpha positive. So we just set alpha equal to this as earlier, and therefore that is what I get in the gradient descent. So if I substitute it back, if I substitute this back, then essentially I am doing xt minus eta times gradient, and assuming that eta is absorbing all the scaling factor of alpha. Right? Whatever is the scaling factor, I'll decide eta separately. Right? So that is one motivation for gradient descent, which is that in the vicinity of xt, I am at xt, in the vicinity of xt, I try to find approximately, let's say first order approximation, I try to find the value, the point where f of xt plus eta d is minimum. Right? I've tried to find the direction also and eta also. The eta is defining my radius, so I just try to find the direction. Okay. That is the greedy search motivation for gradient descent. And if you have followed this carefully, you can imagine that instead of making first order Taylor series, I can make second order also. Right? That will give my rise to another more accurate algorithm. Right? Of course, it will be more accurate at that iteration, but it will also be more complicated to evaluate. Right? That direction would also be more complicated to evaluate. So there is a trade-off right there. You either go for a very accurate solution at that iteration, right? Or you go for a very inaccurate solution at that iteration, potentially taking more iterations because your solution is inaccurate at that point. Or you go for a very accurate solution at that iteration, but potentially taking less iterations till the end. Right? So that is always a conundrum between, let's say, gradient descent and the other algorithm I'm mentioning. It's called Newton method. So Newton method versus gradient descent, that is the pros and cons. One is more accurate, the other takes less iterations. One is less accurate at every iteration, other takes less iteration. Okay. Another way of thinking of gradient descent is local quadratic approximation. So this is a local quadratic approximation of f around xt, but is not Taylor series, just a approximation. So I'm saying that f tilde of x is essentially fxt plus x minus xt transpose f gradient fxt plus this term. Right? So this kind of approximation would look something like this. Right? Either it would look something like this or it would look something like this, depending on choice of eta. Right? If I make eta to be, like if this term is very small, so eta is large, then this term is very small, then it will be very flat. And if this term is very large, then eta will be like this. Like the function will be like this, very steep. So the next iterate in gradient descent is always the solution to this optimization problem. Again, a quadratic optimization problem, so you can solve it analytically, but the xt plus 1 is always given by this arg min over x of this. And what is the solution of this? Just differentiate, take gradient with respect to x. You can see that you will get this solution. This is the gradient. Set it equal to 0. You will get x equal to xt minus eta t times gradient. Right? So this is another way of interpreting gradient descent. Right? Even if you use gradient descent automatically from some library, it is immensely beneficial to understand what really it is based on. It's based on this kind of second order approximation. And therefore, if ever you come across a situation where this is not true, for a function for which this is not true, you know that gradient descent cannot be used or should not be used. Okay, any questions? Like I have till 120. Okay. Okay. So let's take a simple example: x minus 1 square plus y minus x square square. Right. So this is a specific function. It's called Rosenbrock function. It's like just for study. It's a non-convex, not a well-behaved function. It's actually quite a complicated function. But we know that its optimum is at 0, right? Because there are two square terms. So analytically, you can solve it, right? Two square terms. If I take x equal to 1 and then 1 square is also 1, So both of them will be 0. So optimum value is 0, occurs at x star equal to 1. So this is how it would look like. And if I run gradient descent on it, the gradient descent, let's say, starts here, and it would take this path. So I have run gradient descent on it with eta equal to 0.02. And my goal was to ensure that fxy is less than 10 power minus 3. I already know that it should be 0, but I want to reach till 10 power minus 3, some accuracy level. And it took me 375 iterations. Right? This is just a Python code that I wrote, and I ran gradient descent on that Python using that Python code and counted the number of iterations. Okay, with this choice of eta. Now, let's say you run it for some function and you find this. What is your what can you observe from this and your knowledge of gradient descent? Perhaps you could say that 375 is too large. I want to reduce it. How can I reduce it? So though both are correct. So first of all, you should choose a different initial point. But generally, we don't know what to choose. We generally choose it randomly, right? And let's say that we could of course use a different direction, which amounts to using a different algorithm. So let's consider only gradient descent for now. We'll look at you can use another algorithm which would use a different direction. If we use only gradient descent, then we have the only choice that we have is varying eta. Now what is happening here, if you look at these lines, these lines are showing where each step is. So what is happening here is that even though I am going in the direction of steepest descent, I am going too less. I mean, I'm not going sufficiently far. So which means that I should go sufficiently far. I should go further distance. So therefore, I should increase my eta. I increased eta to 0.1 and it took 71 iterations. Right? So this is good. We used our intuition to reduce the time. Now, should we use our intuition more? Right? So I can increase eta to 0.15 and now it takes 45 iterations. But now what is starting to happen is that instead of a straight or almost a curved path, now it is somewhat zigzag. Right? But we reduced it to 45. So I have this thing in my head telling me that try some more. Maybe we can get to 20. Right? Then I increased to 0.2. And now after 5,000 iterations, it is still oscillating. Right? So suddenly from 0.02, it was almost fine till 0.15 and then it broke down. Right? So this is typical of most of the algorithms. They work till a point and then they stop working completely. And if it's really your bad luck if you just started with 0.2. Then you will think that, algorithm doesn't work, maybe I should use a different algorithm. While you should have thought that maybe I should use a smaller step size. Right? So what I see in many students is that they are too aggressive and they use a large step size. Try with a smaller step size. Right? So I'll give one more example. So this oscillation behavior. Right. Average is at the optimum. Yes. Correct. We can do. That's more advanced. I'll not mention, but we can do that. Yeah. Right. So the lesson here is that use a step size which is not too small, but small enough. There is also another approach to doing this, which is to choose a step size differently. For example, this case, there is a diminishing step size, right? It decreases with t. So as I get larger and larger number of iterations, I decrease my step size. But then now this is really difficult to tune. I have tuned it to 0.18 t raised to a minus 0.5. But this is really difficult because I don't know how many iterations I'm going to take. I mean, after all, my goal was to take as few iterations as possible. So I cannot say that I'm going to take 40 iterations, right? So each time I run it with a different value of 0.18, like different value here and different value here, I need to tune it and see how many iterations it took, right? So then the problem with which happens with this kind of diminishing step size, often used in ML, is that it is really difficult to tune. You really need to run it many, many times. Right? So this is difficult to tune eta t. So if I conclude this discussion on vanilla gradient descent, it is definitely simple to implement as long as you can calculate the gradient. It is applicable whenever function is differentiable, because then you can calculate the gradient. Works for large n with low memory requirement. We didn't discuss it, but you can imagine that no matter how large n is, even if n is 1 million, all you need to do at every iteration is calculate the gradient. Suppose there is some function that can calculate. So you have a 1 million dimensional variable, right? What you could do is you can maintain one xt, 1 million dimensional. Each time you calculate the gradient, each entry of the gradient, you can subtract eta times that gradient entry from that entry. So you don't need to maintain several vectors of size 1 million cross 1. Just need to maintain one of them. And you do operations on that only. Right? So you can basically start first iteration, start changing. Once you are done, you calculate your gradient again and then start changing from the top again. Or you could randomly change entries here and there. That's also possible. So that's the like a parallelism that gives rise to parallelism. So the memory overhead of gradient descent is really low, and you can really scale it up for very, very large n. And if you talk about the order complexity is order n, because n is the number of entries, so order n. But it is therefore that's why gradient descent is widely used. And the downsides are, of course, that if you take large n eta, then it may oscillate, and slow eta, it will converge slowly. Either it is slow or oscillate, and you have to really find the sweet spot between the two. So it may converge too slowly for small eta and oscillate for large eta. And another one technique that sometimes people use, is not widely used, but sometimes it is used. At least in theory, it is good. In practice, not so much, which is line search of eta. So what you could say is that when I'm trying to select my next point, instead of picking one eta constant, I will just test out a few values of eta. Not many, let's say 5, 10 values of eta, and pick the one that is best. And then again, next time I'll do that. So your requirement complexity increases. Therefore, each iteration you need to search for different values of eta. But then it could reduce the number of iterations significantly and prevent oscillations, right? So yeah, I'll come to that. Yeah, I'll come to that. So ideally, you can choose eta t to be such that argmin over eta f of xt minus eta gradient. Right? I am essentially now again, each time I have to do something, I pose an optimization problem, right? So I have to solve this optimization problem now at every iteration. Obviously, I'll not solve it exactly. I'll again do some approximation. What I can do is that essentially consider this as a 1D search and do a grid search on eta. Right? I could say, okay, let me search 0.01, 0.1, 0.2, 0.15, some 10 values, and takes the one that is minimum. There are also slightly more complicated schemes called line search schemes. There are few, 4 or 5 schemes. But the downside here is that line search itself could be costly, right? Because in each of these, you need to calculate f. right? You need to calculate f for a particular value. Now at every iteration, instead of calculating f once, you are calculating it 5 times or 10 times. So that is 10 times more complexity. So this will only work well when f can be calculated very easily. If f calculation of f itself is complicated, you better not use it, right? Yeah, this solving this problem is called nine such. So like a 1D, so I did not discuss one-dimensional algorithms. There are some other optimization algorithms which are one suited for one dimension, right? So those can be used. How do you decide when to do and when not to do? There's no way around it. I mean, you don't know when to do, right? So you either do it every time or not do it at all. In general, you cannot have. If your specific function has some, then maybe you can try. But in general, there is no such conditions. So bad is two types of bad, right? Either not converge, so then you definitely cannot choose it. But slow, you can work with, right? So slow is what you have to compromise. Yeah, yeah. So these are, yeah, very good questions. So she's saying that, eta choosing eta seems to be very complicated because I need to tune again everything. You may need to run the optimization algorithm again and again. And these are all very practical questions. This is what happens in practice. In practice, it is never, very fun thing that you just apply gradient descent and it works. It never works like that. Yeah. What is adaptive modifier? Yeah, we'll come to that. Yeah. So what he's asking is that in sometimes you do some adaptive modifications in ML context. Let me just say that all of those are essentially thumb rules. Someone said maybe it works better like this. Someone tested on two problems, and then a lot of people are using it, and it may turn out it doesn't work better like this. People are just using it. All of those are thumb rules. Nothing, nothing set in stone, or nothing even proven empirically or analytically. There's just, guesswork, essentially. It works in, let's say, you could say that, okay, it works for image processing. That way it could say, but you can't say that it works always or in every situation. Okay, for image processing, CNN, then CNN it works. It may be like that. So specific classes of problems. Right, so that is the downside with line search. And essentially the motto is that you find a reasonable value and go to next iteration rather than fixating on one that particular iteration. Okay, so just let me conclude this. Here I was doing grid search based methods, and it was taking the fewest number, 35. So far we've never had 35 iterations. But if you count all the function calls, that is much more, 348, not 10 times. And here the oscillations are of a particular kind. Actually, you can prove it mathematically also. The oscillations have a particular property that they are orthogonal each time. So from one to next iteration, it is orthogonal, then next iteration, it is orthogonal. So it's really zigzagging behavior. No, under any line search. Under any line search, properly you have done it. Suppose you have found the optimum at every iteration, then it is going to be optimal. orthogonal. The termination conditions, you have seen one kind of termination condition, which is function being very small. Now, the again downside of this termination condition is that every iteration we need to evaluate it. You can maybe skip for a few iterations, but still you need to evaluate later on. Another common one that is used is you just run it for 1,000 iterations and that's it. Whatever is the value, that's the value. Another is relative improvement. These are more complicated ones. Gradient magnitude. Oh, I should have put a norm here. So norm of the gradient less than something, because you are anyway calculating the gradient. Just take the norm and make sure that that becomes small. That's another one. If there are multiple local minimums, this we didn't discuss so far. Suppose you have a function which has multiple local minimum, then that adds one more step of complexity. Your gradient at local minimum will be close to 0. So you have already converged, everything works. But if you suspect that this is not a good local minimum, then what you should do is you should restart the algorithm with a randomly chosen initial point, x1 or x0. That should be randomly chosen. And you do it, 10, whatever number of times you have time, that many number of times you repeat. And whatever is the smallest local minimum that you have obtained, that is your solution. Right? So that's what we do in practice. We tend to repeat if it is possible to repeat. So these are the references for the gradient descent. Now my time is also up, so we'll continue in the next class where we'll talk about stochastic gradient descent and also some analysis of these algorithms theoretically. And also, like I'll share the codes with you. So that will be tomorrow. Thank you.